Good morning. Okay. Let's do it. Lecture 4. And I forget to mention this. I always mention it during the summer class. We have 10, 10 actual lectures, and one of them's a half lecture because of the midterm. We lose one for a holiday and one for the final exam, or else it would be 12. So each lecture is 10% of the class, meaning after we're done with today's lecture, we are 40% done with the semester already. If you're not staying up on those, oh shoot, I forgot to prep my email. I got distracted with other stuff. If you're not up on all of your stuff, it's easy to fall behind real fast. So some stats. 44. Hey, they ain't so bad. I mean, it's not. Could be better, but 44 if y'all finished the finished task 1 before the expected deadline. Which, I mean, I'll take it. But out of 59, one person submitted, but no, 2 people submitted but did not finish it. That would bring us up to 46. So that means 13 didn't even make a submission before the expected deadline, which just baffles me. Like it's a pretty big percentage of the course. It's over 20% of the course didn't even submit task 1 before the expected deadline. And at that point, they're just not trying. They're going to fail. And I meant to prepare an email and send it out to all of them. And I forgot to do that this morning, so I'll have to do it after lectures today. Okay, so we're done with Intro to Java. We're done with Intro to Java Part 2. Done with unit testing and classes. Let's talk about it. Let's dive in. Open the directory and then open it. Learn all the little quirks. Relearning. P. Objects and classes. Let's just dive into it. The summer moves fast. I keep saying that, so let's get right into the content and not waste more time. Goodness, it's 3 minutes in already. And not waste more time with intro stuff. So, classes. This is what we want to talk about today. I mean, we've been talking about classes already, but what we really want to focus on today are objects that we're going to write classes that are used to create objects. Whereas so far, all of our classes have been collections of static methods. We're going to see the usage of classes to be able to create objects at this point. So with ArrayList, we did this new ArrayList, and we called this special method that I call the constructor. And we didn't really know, I didn't really talk about what all that was doing. I just said, don't worry about it. This is just how we create an ArrayList or a hash map at that point. But now what we want to do is go to the other side of this. We want to look at what's going on the other side and actually write our own constructors so we can create our own objects of our own types instead of only creating array lists and hash maps and asterisk strings as objects on the heap. We want to be able to write our own classes, our own types, and create our own objects. So let's see how to do that. We're going to write a class that's used to create an object, which is dare I say, the primary use of classes. The way we've been using classes the first 3 lectures isn't really, it's not really what we use classes for. That's just a way to use classes to kind of pretend that we're doing 115 stuff, and it bridges the gap between 115 and 116. But now we got to get into 116 content proper, which is objects. We're going to do objects all semester, all the rest of the semester, which is 4 more weeks. It's not going to be too long, but we're going to be using objects a lot. So to show objects, we're going to use an example. We're going to create a player class, as in like a player in a video game, that's going to have maximum hit points, current hit points, and name. So these are the 3 uh, things, the 3 properties, the 3 variables that our player is going to have, and we want to be able to capture those 3 values in a player object. That's what we want to do here. And here's our class. I'm just going to throw the code at you, and then we'll spend quite a few slides explaining what's going on here. So to create those 3 variables, well, we could, now first of all, we could just like write a method that declares 3 variables and then uses those 3 variables without objects. But that will get messy very quickly, especially when we want a multiplayer game where multiple players exist. Now we have to have max HP 1, HP 1, name 1, max HP 2, HP 2, name 2, max HP 3, HP 3, name 3, and that's going to get cumbersome. That's going to get annoying really quick. So what we want to do is create a class that's going to be used as the blueprints to be able to create objects. And we can create as many objects of type player as we want, just like we can have as many objects of type array list as we want. We're just going to create new player, new player, new player. So we're creating an object of type player. We're going to write a class of type player to be able to create those objects. So this class is going to be a collection. Every class is a collection of state and behavior, where the state is all the variables associated with that, with objects of that type, and the behavior that's all of the methods associated with objects of that type. So like array list, your state would be all of the values at each index, which is actually represented as an underlying array, which we will actually look at later in today's lecture. And the behavior is like .size, .get, .add, all the methods that you can call on an array list. That's what we want to do here, is we want to create a player that has all of its state, all the stuff that it remembers, and all of its behavior, which is the collection of methods for that for objects of that type. So the variables. Let's start with the variables. We declare these just like any other variable. They have to have a type and a name. Type name, type name. I'm not assigning these any values right now, but you can do int 8 max HP equals 20 or whatever value you want to give them if you want them all to have the same initial value. We're going to talk about that in the constructor a little more, but we don't have to. In Java in general, you don't have to assign a value to the variables you declare. We usually do, but with these types of variables, we don't always. And I'm going to call these instance variables. Morning, Dave. We call these instance variables when they're part of a class like this. When they're going to be variables that belong to objects of this type. I'll call them, and let me specify, I'll call them instance variables in CSE116 because they belong to each instance of this class, which is an object of that class type. We instantiate the class, we create an instance of it that's going to be one of the objects, so I call them instance variables. They belong to instances of that class, not the class itself. These come by many other names. State variables, that's what I used to call them. I try to pick the least confusing thing to call them in 116. State variables because they're the state of the object. I switched to instance variables. I might start calling them object variables. I don't know if anybody else calls them object variables, but I might start just because it's more clear what they are. And then my favorite thing to call them is actually fields. If you take an upper level course with me, I'll probably start calling them fields, and you'll hear that. I mean the same thing. If you hear any of these things, they're all referring to the same thing. These are variables that belong to the objects of that class, not the class itself. I like fields just because it's one syllable. It just rolls off the tongue easier, but it's probably the least meaningful, at least to me. This comes from the world of mathematics where they call them fields, and we borrow that sometimes. But it really has no intrinsic meaning. You just have to know that field means these variables. So I like it for the brevity, but not for the description. So instance variables is what I'll call them this semester for the next 4 weeks. And usually, I've been pretty good about being consistent with that each semester. That'll call them instance variables each time. And then every time we create a player object, each player will have its own set of these variables, its own copies of all of these variables. And that's very important because if you have a two-player game, especially if it's like a fighting game, let's say you have two players fighting against each other, you don't want them to share an HP variable because you're never going to have an actual winner. They're both going to have their HP reach 0 at exactly the same time because they have the same exact HP variable. You don't want that. That doesn't make sense. You want each player to have their own HP, their own name, so they have their own copies of all of these variables so they can vary independently of each other. So that's why we create these as instance variables. So each object that we create of type player, each player in our game can have different copies of these variables that store different values. And then we're going to get to our very special method that's been foreshadowed for a full week, I guess. Is that true? Last Thursday was the first time we saw new array list, a new hash map. And now we want to go on the other side of that. We want to write a constructor. This is a very special method that's going to be used to create objects of this type. And it's going to be called using the new keyword, just like we did new array list. We want to do new player to create a player object. So we have a special method called a constructor. It has a few unique properties that tell Java that this is a constructor. Just like a main method, you set up your main method in a very specific way. And then that tells Java, hey, this is the main method. This is where the program starts. With a constructor, there's a few things we do. One, the name of the method exactly matches the name of the class. This will be the only method you'll ever see me write that starts with a capital letter because it has to match the class name, which should start with a capital letter. So the proper thing to do is these methods start with capital letters, which is kind of a big clue. You see a method that starts with a capital letter, you're probably looking at a constructor. At least in Java, you're looking at a constructor or somebody with bad naming conventions. And this is the one method we'll write, the one type of method we'll write that doesn't have a return type. We don't specify any return type with the constructor. What the constructor is actually going to return implicitly is a reference to the object that it constructed, but we don't specify any return type. We just don't put one, not even void or anything. Really what it would be is return type player. So I think Java just kind of avoids having us write public player would look a little awkward. So they're like, you know what, let's not. It's always going to be the same as the name of the method. Let's just write the name of the method and we'll figure it out. We know what you mean. And this is what's called. If we say new player, we're saying call the player constructor, which the name of the method exactly matches the class name. So when we call a constructor, it looks like we're using the class, but what we're actually doing is calling that class's constructor, or at least one of that class's constructors. And we use the keyword new, this special keyword new. That means, hey Java, I'm about to call a constructor to create a new object, allocate some memory on the heap, create my instance variables on the heap, do all that stuff. That's all about to happen. And then you call the constructor itself. So we're calling the player constructor, we're calling this method. And then at that point, once you get past the new, the player, the no return type, all that stuff, once you get to the open parenthesis here, after that, it's pretty much a regular method call. You have two parameters in this instance that are string and int. So when you call it, the argument list better be two arguments that are a string and an int. So I'm going to give it some string, whatever I'm calling my player, and some int. It's their initial max HP, which is going to be their initial HP as well. So we're going to create a new player object. This is going to create a player object on the heap. It's going to set its name to the string name. Its max HP to 10, its HP to 10, and then resolve to a reference to the player object that was just created on the heap. Now, a lot of that is just words at this point. It works the same way as array list and hash map, but I think that'll be much more clear, if it's not clear now. That'll be much more clear when we get to the memory diagram. I'll revisit constructing objects, and we'll go into it in a lot more depth with visuals. But just before we got there, I wanted to at least briefly explain everything that's happening with a constructor call. And then the keyword this. Holy crap, the keyword this. We will talk about this all semester too. This can be a point of confusion among students. I don't think it's too crazy of a concept, but it is something that the first time you see it, it's pretty trippy. But we will talk about it a lot. And again, this is another thing that will make more sense in the memory diagram as well. What's up, Jashwanth? Hopefully I'm pronouncing that right. Jashwanth? The keyword this can be tricky when you're first seeing it, though. So let's talk about it. This is a keyword, and it's a keyword that you can pretty much think of as a variable. You know, you can think of it as a variable. Just think of this as a variable. It is a keyword, so you can't create your own variable named this. You'll get you can't use that keyword error or whatever the error it gives you is. But think of it as a variable that just comes out of nowhere. It just appears. It just is there. You can always use this keyword this variable this. And what's stored in this is a reference to the object that called the method that you're currently in. In the case of a constructor, it's a reference to the object that's being constructed. And that's it. That's what the keyword this is. If you feel me on that, if you hear me and understand that, you know the keyword this. Yet it does get trippy, and try to explain it in a way that doesn't get trippy this semester. I think it trips students up who don't go to lectures, my guess. Because by the time we do a few memory diagrams and talk about the keyword this quite a bit, there's not much else I could say about it. You either understand that you just treat it as a variable that stores a reference to the calling object, or you don't. And I'll say that a whole bunch of times throughout the semester. I'll give you tons of reminders all semester about what the keyword this is. So we have a reference to the object being constructed. The dot operator takes us over to the heap, and we're modifying the max HP variable that belongs to this object, but we're over on the heap, not the reference. So this is a reference. Dot takes us to the object, and then we modify the max HP variable for that object, that instance variable for that object. Again, many more examples. We just want to do a high-level overview of classes. In this example, we'll get into a lot of other stuff. And a note about constructor parameters and instance variable initialization. So we want to initialize all of our instance variables to some meaningful values, but what those values are can depend on our specific application, like why we're writing this class is going to inform what we put in the constructor and etc. So, etc. I'm about to explain it. Is any instance variable that you want to initialize to a different value on a per object basis, you're going to want to initialize them in the constructor and let whoever's calling the constructor specify the initial value for that instance variable through a constructor parameter. So with this modified example, what I'm saying is every player in my game is going to have a max HP of 10. They're all going to start at full health, so there's no reason to put that as a constructor parameter because all my players are going to have 10 max HP, but they're going to have different names, like the end user, the player, potentially all the way, potentially all the way to the end user can specify the name of each player, or the programmers, maybe you have a hard-coded roster of characters that the human player can use. So we want all these player objects to have different names that are, pre-coded in the game, but the developers are specifying. But either way, when somebody creates a player object, we want them to be able to specify the name, so each player in our game can have a different name depending on however this constructor is being called. Whether it's the user putting in, punching in their own name, their own custom names, or a bunch of hard-coded names for a predetermined roster, the constructor will still have to initialize those differently for each player. So we have choices there. Usually, at least in 116, those choices are made for you. The homework description is going to say write a constructor that takes these parameters. But when you get out there in the real world, this is something you'll have to decide is what instance variables do I want initialized on a per object basis. Those are going to be my constructor parameters, and anything that's not initialized on a per object basis, I'm going to initialize right when I declare the variables and give them some default values. Okay, and I intentionally skipped over this keyword private because this is a pretty long conversation that we have to have here. The keyword private. So on the surface, private isn't too crazy. Private means, let's get the definition of private out of the way. What takes a long time is, why do we even use private? Why not make anything public will be a question a lot of you will rightfully have. And it takes some explanation of why we even use this. So private, what it is it means that anything that's private, which can be variables or methods, anything that's private can only be accessed from code within that class. So inside these parentheses, I have an open parenthesis and a closed parenthesis defining the class. Any code in between those, braces, any code in between those two braces can access the private variables and methods declared inside that class, and anything outside those braces cannot. It's a very hard line. If you have code outside of these braces, it cannot access these private variables. We can also have private methods. Those private methods cannot be called from outside of this class. Only code within the class can access them. So this .maxHP, I'm inside the braces for the class, so I'm allowed to access that maxHP variable. But if I was in some other class, I create a second class, an enemy class, and I try to access the player's max HP variable, I can't, because it's private and I'm outside that class where that variable is declared. So a few questions. One, there's going to be code outside of this class that wants to use these variables. That will happen, or else our game just doesn't work. That's probably hard to see right now. Coming from 115, I don't even know if you ever write multi-file programs in 115. But multi-file programs, we just call those programs because that's what everything's going to be from this point forward. You're going to have other files that want to access these variables. For example, let me give one quick example. You have your graphics class that's rendering everything to the screen, and you want to be able to get the player's HP and max HP so you can display a health bar to the player. That code isn't going to be in the player class. That's going to be in some GUI class, graphical user interface. It's going to be some graphics rendering code that needs those values to know what to render. Among many, many, many other things are going to need it. Somewhere you're going to have your whole game engine, which is going to control things like combat and health, healing, spells, whatever your game actually is. That's going to need to read these variables and modify them whenever the player takes damage. All that code's not going to be in the player class because it's going to be common to players, enemies, a lot of other classes. So a lot of code outside of the player class is going to need to access these variables. How do they do that if they're private? And why did we even make these private to begin with? We'll answer these questions. So first one, incoming getters and setters. If you've ever coded in Java before, if you did any Java in high school or wherever else, you've probably come across these. Hopefully you came across these because this is the way to write Java code. If you're writing Java code without getters and setters, you're not doing it right. So getters and setters. We have two special methods, get and set. So a getter is going to return, all it does, it takes no parameters and just returns the variable that it's written for. So my get max HP getter is going to return this dot max HP. That's it. It just gets the value for you. Setter, same concept, but the other way. We take a variable of the type matching that instance variable, and we set the instance variable to that value. These return void and take the value that you're going to set, which is our first meaningful void method. So this method returns void, but it does actually have a good use. Unlike that, our first void method, besides main methods, our first real void method was that why method, and I said, why would this exist? Why would you ever do this? That doesn't mean why would you ever use void, because void is going to be very important for the rest of the semester now that we are talking about objects in writing classes that use objects. My dog came like he did on Tuesday. So that's getters and setters, and then getter and setter for each instance variable. So get HP, set HP, get name, set name, get max HP, set max HP. So this is how outside, and all of these are going to be public, of course. So this is how code from outside of our class is going to interact with our instance variables. Now the graphics engine, the combat engine, all those other portions of our code now can access these variables and modify these variables, which, oh, by the way, some people like to call these accessors and modifiers. I don't like the big verbose names, but that is what they're doing, accessing the value and modifying the value, but we can keep it simpler and say getting the value and setting the value. So when they want to get and set these values, they call these getters and setters instead of accessing the variables directly. If you're accessing the variables directly, you're wrong. Don't do it. Don't do it. In Java, I want to make sure I note that. Don't do that in Java. This is the way to do instance variables in Java. In a lot of other languages, like if you watch me write Python code, you'll notice I won't do this. I will not write getters and setters in Python because Python's set up in a different way where the usefulness of getters and setters doesn't really exist. So why would we use getters and setters? Glad you asked. And in a word, control. We want control over our code. And mostly by that, what I mean is we don't want somebody else, like when you're writing code, usually you're on a team of developers and other people on that team are going to be using your code. So when you write the player class, there's somebody's working on that combat engine, somebody's working on the graphics engine, etc. And they're all using your class. They're saying new player, they're saying player dot get max HP. They're calling your methods. And if you make your instance variables public and you don't do getters and setters, they have no choice but to access your instance variables directly, which hopefully I can convince you is very scary. You don't want anybody accessing your instance variables directly in Java. This is a very Java-centric thing. And in other languages, C++ I think still has this feature that this is how it behaves. And you don't want that, because once they start accessing your instance variables directly, you lose control over how your code is being used. So for example, with setters, sometimes you want to sanitize the inputs. If somebody's calling set HP, if somebody's saying player1.hp equals and accessing your variable directly, they can set it to 1 billion or negative 1 billion. They can set it to some really weird values. Usually not on purpose. Your teammates aren't just going to be, randomly hitting buttons and just setting the HP to some ridiculous value. The end users might, because it'd be funny to have 1 billion HP. But your fellow developers who we're talking about at this point, and the end user's not going to have access to the source code, usually. And you don't want them to to do something like that accidentally. Usually it's when they have some like damage calculator. They're crunching a bunch of numbers and some complex formulas and everything. And they missed one of their edge cases where that formula blows up and they get a very large value or a very large negative value either also. And they're setting HP to that value directly, and now we have a ridiculous amount of HP. We don't want that. We want to cap it at max HP. You shouldn't be able to have more HP than your max. So what we can do is write in the setter for set HP, we can do that check. We can say if somebody's trying to set the HP to anything greater than the max HP, just set HP to max. Like they maxed out, they filled up their HP. Nothing left to say about it. But if they're setting it to something less than max HP, just set it to whatever they told us to set it to. We could also have a check for below 0. We could add here as well. But we want to be able to sanitize our inputs. Now, if they're accessing the instance variable directly, and later on down the road we realize that players are getting more than their max HP, they're getting overhealed, there's nothing we can really do about it. We lose control. What we have to do is either send out some emails or walk office to office knocking on doors and say, hey, my code sucks, so you have to fix yours and make your code better. I'm like, well, I have this method. It heals the player 100 HP, so I just added 100 to their HP. Like, what's wrong? What could possibly be wrong with that? And you're like, well, it doesn't enforce max HP, and I would like, you don't want to have those conversations. Just put it in your setter, and you do the check, and now people can't break your code. They can't do those weird things. So sanitizing inputs is a big thing. That you lose that control if you have public instance variables. You can't do this after the fact. But now we make them private, and even if we don't need getters and setters, even if we're not using them, even if set HP just says this dot HP equals HP, even if that's what we're doing at first, it gives us the option to add this sanitation later. We can change our mind later as we add more features to our game. We have that option. So even if we're not even if we're not sanitizing inputs, we can still do that later. But if we just say our instance variables are public, we have no options for the future. We're not leaving our options open. And also with getters, sometimes we want to format the return values. So like get HP is just returning the raw HP. Maybe that's not the behavior we want. Maybe we have a meeting and everyone decides that we want HP to be as a percentage of total HP, because then it's easier to do the health bars. If this returns 0.5, we know we can display a health bar that's half full. So what we can do is still represent all of our variables the way we're doing them, but then when we return from get HP, we can calculate that percentage and then return that percentage. Hey, Piyush. Oh yeah, that was the end of my sentence. I hope it's nice in India right now. It's a little hot over here right now, but hope it's good over there for you. So control, that's why we do this. Other languages, the reason other languages don't do, that's a weird way of phrasing it. The reason why in most languages you don't do this is because a lot of languages have a way to add your getters and setters after the fact. For example, Python, if you have Python doesn't even have access modifiers, so you can't have a private variable in Python. The language doesn't even support private variables. But what you can do is write your variables, and then other people are going to access your variables directly. They're going to say player.hp equals, etc. But then you can write a getter and setter for the variable after the fact that has the same syntax as variable assignment. So you add your getter and your setter, and then all that code that says player.hp equals or print player.hp, that code will then retroactively start calling your getter and setter methods using that same syntax as variable assignment. So you don't lose control in Python because you can add your getters and setters after the fact. Java, you're going to have to write your getters and setters that just don't really do anything. and force everybody to call those to leave your options open because you can't add them after the fact. All right, so that's getters and setters. It's a part of Java. It's kind of annoying. If I'm being honest, it's kind of annoying, but it's for good reason. We're going to be good developers, do things the right way. We're going to use our getters and setters, and we're always going to have private instance variables in Java. Sometimes, actually not even this semester, but sometimes we'll use protected instance variables, but never public instance variables. Not going to use public instance variables. Private instance variables. Okay. We get through that. Well, I like giving the explanation there. When I first learned getters and setters in lecture, they're just like, use getters and setters. Grr. And they didn't really explain anything. So I like giving the explanation because it is for good reason that we use getters and setters. Even though it is annoying, it is for good reason. There's a good reason why we do that in Java. And why we don't do that in other languages. Then you have the option, once you have your getters and setters, is in your constructor. You don't have to do this because you control this code. You can always change it after change your mind later. But you can call the setters in your constructor instead of this.maxHP equals max HP. You can call the setters, especially useful if you actually have some sanitation checks. So like set HP. Actually, it doesn't make sense in this case because HP is exactly max HP, so we know this logic isn't going to do anything. But in your task 4, is that 4 already? It should be task 4. What am I missing? Task 3. No, task 3. Task 2. Wow, that comes so early. In your test 2, for your ratings, you have the sanitation for your ratings. It has to be a value 1 through 5. And if it's outside of that range, it's an invalid rating. You have to do that check in your set rating and your constructor. So it can be helpful just to have less code that you have to type to, in your constructor, call your setter so you can reuse that sanitation code and not have to cut and paste it into your constructor. And then if you have a bug, you fix it in one place, you forget to fix it in the other place, which is very common when you have duplicate code like that. You don't want to get in a situation like that. So calling your setter in your constructor is going to be one less potential headache that you have to run into. But if your setter is just this.maxHP equals max HP, you can just duplicate that line up here. It's fine. And I never use the keyword static in any of this code. So we got public and private. We got that conversation there. All these conversations where I'm like, oh, we'll talk about it Thursday. We'll talk about it Thursday. We're talking about them all. It's Thursday. Public and private, we got out there. Classes versus objects. Writing our own constructors. Instance variables, I didn't really allude to them. But static versus non-static. Let's do it. Nothing in here is static. So the difference between static and non-static methods and variables is static methods and variables. We didn't see any static variables. We'll see technically two of them today, but in the same example. But we can have static variables. But we did see a lot of static methods. So static methods and variables belong to the class that we're writing. The class. So if we had any static methods in this class, they belong to the player class itself. The average method belongs to the problem set class. Those belong to the class. If they're not static, if you just don't use the keyword static, which I'll call non-static methods today, but in the future I'll just call them methods because those are the more regular methods in Java. If we have a non-static method or variable, those methods and variables or state and behavior at this point belong to objects of that type. So when I create non-static methods, this getMaxHP method belongs to objects of type player. So when you say new player, you're creating a player object from that class. Your class is your blueprint to be able to create objects. When you say new player, you create an object of that type, player, and then you do that object dot get max HP. You're calling this method from an object, not from the class itself. So instead of problem set dot calling a method from the class itself, because it's a static method, so it belongs to the class, instead you're saying new player, player one equals new player one, a reference to an object, dot take me to that object, then get max HP, set HP. You're calling those methods, those non-static methods, through objects of that type. So static belongs to the class, non-static belongs to objects of that type. Ooh. Oh, puppy. Scared my dog. And when we write a class, we are defining a new type. I'm saying objects of that type. What we're doing is creating our own type in Java. So like ArrayList was a type, string is a type, int is a type, though it's a little different because it's a primitive. So what we're doing is creating our own player type. So the player class defines the player type. Just like we have variables of type ArrayList, and the ArrayList class defines that type. We went to the ArrayList class. I think we did that in maybe we didn't do that in this lecture. But there's an ArrayList class that defines the ArrayList type, so we can create variables of type ArrayList. Same thing here. We created a player class, which means we can now use the player type, which we can use anywhere where we used any of our other types. That's as a variable, so I can have a variable of type player. Parameters are variables, so I can have parameters of type player. I can have methods that return values of type player, which is actually a reference to a player object, but I won't always say that every single time. That'll be implied, but explicit when we do our memory diagrams. And as type parameters, so I can have an array list of players. I can use this anywhere where I could, array list or string or capital I integer, capital D double. Any place where we could use any of those types, we can use our new player type because we just defined a new type in Java. When should we use static methods? Almost never. So we use those in the beginning just to kind of pretend that we had functions, but just to bridge the gap from 115 to 116. But now that we're learning classes and objects, everything's going to be objects from here on out, and pretty much nothing's going to be static anymore because we're going to mess with objects. We're doing object-oriented programming, so we're going to be messing with a lot of objects, which means very little static from here on out. There will be, but to more directly answer your question, when would you use static methods? It's if you have a method that doesn't rely on any of your instance variables, that's your clue that that should be a static method. So we want these methods to, methods are modifying and accessing the instance variables, so they have to belong to an object of that type, because how else are we going to access the instance variables of an object unless we belong to that object? So that means these have to be non-static. So any method that uses the instance variables, the state of that object, has to be non-static. But if it doesn't use any of them, usually that means it's a helper method, and you're going to, and you can have that be static. There are a few exceptions, not to what I just said, but there are a few exceptions to everything's non-static from here on out. There are a few methods, mainly on task 6, that don't use any instance variables, and those methods are going to be static because, well, they don't use the instance variables. There's no reason for them to be non-static. So we will see a few outliers that are static from here on out in the future, but mostly from here on out, it's going to be non-static methods. There's one more thing I was going to say, but I'm not thinking of it, so... Yeah. Okay. And when we're talking about memory, our primitive values, our primitive types are stored in our variables as values. So lowercase d double, lowercase I int, lowercase b boolean were the three we talked about. I'll throw in char. I very briefly mentioned it in a bullet point on a slide, but I didn't talk about it at all. But char, it's a single character, usually of a string. At least in 116, we don't put a character in a variable directly. But lowercase c char. All of these primitive types are stored directly as values. So if you have a variable of type double on the stack, its value is stored directly on the stack. The value stored in that variable is literally a double. It's that 64-bit format that we saw last time. It's those 64 bits. That's what's stored in the variable. Same with an int, except it's 32-bit values, 32-bit integer, 1 bit for the sign, 31 bits of binary for the value. Char is an 8, well, we don't have to talk about all of them, but it's an 8-bit value. Is that true? Oh, that's not necessarily true if it's UTF-8, if it's not an ASCII, but I don't want to go down that rabbit hole right now. And Boolean is your true or false. Those values are stored directly in those variables. Anything that's not a primitive, anything besides your primitive, so every other type, including every single object of a class that you wrote, everything else is going to be stored by reference. Just like your array lists in HashMap or your list and dictionary in Python, everything else is going to be on the heap, and what's stored in those variables is a reference to that object on the heap. So everything besides your primitives, which we'll still use, of course, everything else is stored by reference. So that heap, ooh boy, get used to using that heap because there's a lot of it coming up the rest of this semester. We're going to be doing a lot of heap work. There'll still be, obviously the stack's still used, but our values are going to be references to objects on the heap. We're going to do a lot of heap. And then a few asterisks. I talked about string quite a bit already this semester. Our auto box types also are technically objects on the heap, and the compilers can be pretty advanced that where these values actually end up might be different than the way we trace them. But the way we trace them is how they behave, and as programmers, that's really what we're concerned about. How does our code behave? And the way we're doing our memory models with our stack and heap is going to be how those values and variables and objects behave, and that's going to let you know if your code's going to work or not, how your code's going to work, how your program's going to run. Even if the compiler has some crazy optimization that puts your strings on the stack or does something weird, we're not going to be concerned about that. Like your autobox types can be compiled down to primitives and be stored by values. Even we're going to ignore all that. If it starts with a lowercase letter, it's directly by value. If it starts with an uppercase letter, except string. And I'm never going to ask you to trace these autobox types anyway because I don't want to open that can of worms. Everything that starts with a capital letter except string, those are going to be stored by references to the heap. Every single one of them in 116. All right, and let's do this. Memory diagram. Just make sure I get the right one. Yep. Go to our code here. Week 4. Well, that's why I was tripped up on the names, because it's week 4, not task 4. Simple player. That's the one. Sorry, I zoomed in one more level last time because there just wasn't a whole lot of code. And we need the heap back. There you are, heap. Being coy and hiding like that. We need the heap for the rest of the semester. Yeah, I don't think there's any examples for the rest of the semester that don't use the heap. And most of them use the heap extensively. Right, I gotta stretch real quick. Oh, my shoulder. Alright. Let's trace this thing. So every memory diagram from the dawn of time has started with a main method. Main methods are still static because they're called from because they're wait, why? I lost my explanation. My first two explanations were wrong. That came to mind. Because they're called without creating an object first. We can't create an object of a type and call a constructor before our program even runs. It just doesn't work like that. So a main method always has to be static because this is our first entry point before we even have anything on the heap. It has to be static because it's going to be called through the class itself because we have no objects of that type until we start running code and creating objects. So our main methods are always static for that reason. That's why the main method was static. It's public, so we can call it from outside of the class. The simple player class, there's nothing in here that's calling the main method. It's being called from outside this class via magic or whatever Java's doing to call our main method to set up the program and the stack and everything. So it has to be public because it's being called from outside, and it returns void. We don't call a main method for the return value. Some languages return an int from their main method because they just can return error codes to the operating system. With Java, the main method is being ran by the JVM, and then the JVM is going to talk to the operating system for us. So we're not returning those error codes directly. The JVM would handle any crash of our program for us without reporting directly to the operating system. So we're at a point where we understand all three of these keywords. We have public, static, void. All three of those should be, I mean, we just talked about static, so that should be a little fuzzy still. Public versus private, we talked about it a bit, and I'm kind of done talking about it. Static, there will be more things we have to talk about, but you should have a pretty decent understanding of all three of these at this point. Takes a long time to get there from day one going, don't worry about these so much now, to you should have what you need. Okay, and what was I saying? The main method, so every program starts with the main method, and usually, that's not too much to think about. You just start at the main method, and that's still true. But as we get more and more code in our classes, it does, there's something, 18 plus years of starting at the top, like reading or anything ever. You start at the top and go down. You kind of have to break that way of thinking and look for the main method, which by convention we usually put as the last thing in our classes. The convention actually is all non-static stuff and then all the static stuff. But if we have static stuff, it's usually just the main method, so the main method ends up being the last thing. And even if I have other static stuff, personally I like to put the main method last. So usually if you're reading code from anywhere, it's pretty consistent. Developers are pretty consistent with this one. If you're looking for a main method, scroll all the way to the bottom. That's probably where you're going to find your main method. So everything starts with the main method no matter where it is in the code. But it does still start with the main method. So main, and then P1. So we're declaring a variable P1. Man, my timing slips. 54. How did we get to 8:54? And I'm just starting the memory diagram. Well, let's keep going. The pace will not let up, and I gotta actually increase the pace here. Simple player. I guess I gave you a long explanation for getters and setters, but I like doing that explanation. It's not it's time well spent, in my opinion. So we have the variable player1 being assigned something on the right hand side. So the variable, we've seen that before. And then the right-hand side is going to be the return value of a constructor call. We have the keyword new. This was true with array lists and hash maps, but now it's a bit trickier, so we have to think about this a little bit more. But the keyword new means we're creating a new object on the heap. We're asking the operating system to allocate memory for that object. Whenever we see the keyword new, that's your clue. That's how you know you will be hitting this button right here and creating a new object on the heap, because that's what the keyword new does in Java. It's going to create a new object on the heap. When we create an object on the heap, we specify the type. So simple player. I guess what makes it simple is I deleted the a couple getters. Just so it fits on the screen, or else I wouldn't be able to fit it in the tracing tool. But it's basically the player class that we saw in the slides. So we specify the name or the type of the object. We're going to map the constructor. If you click the constructor button here, it'll give you a drop down of all of the frames on your stack, and you want to click the one that corresponds to the constructor for that object. And what you get is some nice color coding that way. It makes your traces easier to read, and it's easier for you to track through your code and make sure you don't have any I don't know, it's just easier for you to find if you made any little mistakes in there. Plus it's easier for us to grade when everything's color coded. So map your constructor and then create your instance variables. This is something we haven't ever done with array lists or hash map or list and dictionary in Python, is adding our instance variables to that object. So we usually do like name and value as index and value or key and value, but here we're going to use them for their actual intended purpose, is just like variables on the stack, name and value. These are going to be the instance variables for that object. So whenever we create a new object of type simple player, we're going to get copies of all of our instance variables, or any class, but simple player in this example. We're going to get copies of all of the instance variables. So you look through the code, and any variable that's declared outside of all of the methods of that class, and by convention the variables will come before all the methods. So look at the top of the class and look for any variables that are being declared, and you get copies of all of those variables in your object. So we have max HP, HP, and name. We have copies of all these variables, these instance variables, in the object that we just created. And we're not giving them any values yet. Technically, they do get default values. The default value for int is 0, for example. So technically, they got assigned 0. If you put zeros here and then cross them out when we get to the constructor, that's fine. But I'm just going to leave them as uninitialized in the trace. And leave it at that. Or else we have to memorize all the default values for every object, which are pretty much what you would expect them to be, empty string, but we don't have to mess with that. So we get copies of all the instance variables, and then we're going to call the constructor. Remember, the constructor is a method call, and I don't know why, but this really trips students up all the time. So just, I'll give my standard advice here again. When you're doing your memory diagrams, you will don't overthink them. Turn your brain off a little bit and don't overthink it. So the constructor call is just a regular method call for the most part. There are some differences, but treat it like a method call, meaning you take the parameters and assign them the values of the arguments. What a lot of students will do is they'll see a trace like this, and they'll put HP on the stack as though it were a parameter, because it's an instance variable, so it must also be a parameter. That's not the case. Your instance variables do not automatically go on the stack. I don't know why I see that all the time, but I do see it. I have an idea of why, because a lot of my lecture examples do initialize every instance variable in the constructor. But I'm skipping a step. We can't do that yet, because so this isn't an IDE right here, if you're asking this. The IDE we use for the class is IntelliJ. So I'll use I was in here for a second. I'll use IntelliJ for the IDE for the class. Yeah, I must have had IntelliJ open when you asked that. Which I recommend. It's my favorite IDE for Java development by a long shot. This. So I'm skipping one big step, and this is a huge one. This one we gotta focus on a bit here. Every single non-static method call, every single one of them, every non-static method call, so most method calls for the rest of the semester will have the keyword this as part of their stack frame. So whenever a non-static method is called, when we do our traces, we're going to have the keyword this as the first thing, usually the first thing in the stack frame. The order, if you get your stuff out of order in a stack frame, I'm not going to care in terms of grading. I'll care, but I'll be like, it's fine, it's fine. But the first thing, I always put as the first thing to make sure I don't forget it, is when you call a non-static method, put this in the stack, and this stores a reference to, in the case of constructors, the object that's being constructed. So this stores the value OX100. This always stores a reference to the calling object. For a constructor, technically the calling object is the object that's being constructed. So this stores a reference to the calling object. Every single non-static method call will have this in its stack frame. If you're doing the OOP quiz and you don't have this in your stack frames, that's an easy way to fail that quiz. This is in the stack frame. Some languages, like Python, make this explicit and actually put it as a parameter in every single non-static method. Java doesn't make it explicit like that, but it is there. It is a parameter to every non-static method. There is an extra parameter that's invisible to us. That's the keyword this, that stores a reference to the calling object, the object that called that method. And this, literally the keyword this, is the difference between methods and functions. A method has this extra parameter that has a reference to the object that called that method. Functions do no such thing. There's no calling object. There's no calling class. You just called the function straight up. So the functions don't have any hidden parameters. Methods do. They have a reference to the object that called that method. In Python, they're not hidden. It's not hidden, but it's still a method because a method is called through an object or through a class. Static methods are still methods and has a reference to the class itself. But it has that extra reference that is the context for that method call, which for our purposes is the object that called that method. So this stores a reference to the object that called that method. And then we can do our parameter stuff. So our parameter stuff is as usual. Name gets the value from the parameter list. And then max HP gets the value from the argument list. Sorry, I said parameter list. Argument list. Max HP. So that part's a regular method call. Notice that HP is not a parameter here. It's not a local variable. It's not declared anywhere. The code's not telling me to create a variable HP in the stack frame at all. It's only telling me to create HP in as an instance variable for that object. So I have HP over here, but not over here. If I had this exact example as a quiz, a staggering number of students will have HP in this stack frame, even though the code does not tell you to do that at all. And I kind of see the confusion. I think I have to have more lecture examples like this where it doesn't matter. We're not there yet. And then we can run the code. So this is a regular method call. We're going to run all the code between the braces. So the first thing we do is this dot set max HP. So this resolves to OX100. Dot means, hey, reference, take me to your object. And then from this object here, we're going to call set max HP. So from this object here, we're going to call set max HP. This object is going to call set max HP. So we're going to create a new stack frame for set max HP. That much is familiar. We've done that a billion times. But set max HP is a non-static method. So we have this, which is a reference to the object that called that method. That object was called from this, or that method was called from this object right here, which has a reference OX100. So this is OX100. Every non-static method call has this as a keyword that stores a reference to the object that called that method. So when we follow our dots, whatever object we're at when we call that method, that's the reference stored in this. Very important concept, this. When you're reading code, I think that this, literally the keyword this, is one of those concepts that's pretty hard to understand just by staring at code examples all day. But once you do the memory diagram, once you see the memory diagram of how it's all mapped out, the keyword this, I think, gets a lot more clear. It's one of the huge benefits of doing these memory diagrams, is the keyword this, because it seems like magic when you look at code. It's a keyword that comes out of nowhere and it's just there, and it, it's confusing. The memory diagram, I think, really sheds some light on it. Then we're going to call this method parameters max HP. Gets the value max HP. This is resolved from within the constructor stack frame. That's where we're at when we're resolving this argument, max HP. So we go to the constructor stack frame. Max HP is 10. And that's important, getting the right variable here, because we have a max HP right here that hasn't been initialized and is technically the value 0 right now. We don't go to this max HP. We go to this max HP in the stack frame. Each expression we evaluate is going to start at the stack frame. So this expression, this dot set max HP, starts at the stack frame but ends up heading over to the heap. But then when we resolve the argument, that's a separate expression. We start over again at the stack frame and we find max HP right away. So just because the method call is over on the heap, by the time at the time we resolve max HP, we're not at the heap at that point. We're still in the stack frame. So kind of a nuanced point. That one is a bit trickier, knowing when to start over at the stack frame to resolve a value. And then set max HP, this dot max HP. So this is the value we're assigning, equals max HP. That's a separate expression. So we start over at the stack frame again. Max HP is 10. So this is going to get the value 10. Which, just looking at the code, that's what you would expect to happen. I hope that when we say new simple player Dark Cecil 10, that you're going to get some object with a max HP and HP of 10 and a name of Dark Cecil. But we want to make sure that we go through all the steps to know exactly how that's working. Because if we understand exactly all the mechanics of how this program runs, it's going to help you understand how the more complex programs run, and how to do your homework code when your homework methods get a little bit more complex too. You're going to know how to do those ones. And that's the end of our setter. Return, go to the next line of the constructor, set HP, and it's the same thing. We kind of just run it back 3 times here. Set HP, this is a reference to the calling object. We did this dot set HP. That was from the object OX100, and that the references are easy here because, well, there's only one. It's always going to be OX100 until we get to the second one here. So we kind of can't get it wrong at this point. And create a variable, HP is 10. Is max HP, which is 10 in that stack frame. Set HP, if HP, which is 10, less than or equal to this dot max HP, which is 10, that's true. So this dot HP equals HP. This dot HP equals HP from the stack frame, 10. This returns. We do the same thing for set name. Set name was called from OX this dot set HP, or set name is called from CSE116. We have a variable name, which gets the value accessel, and this dot name equals name, and then returns. So notice what just happened here. Another subtle thing just happened here is we just called 3 methods that return void. So we didn't call these methods for their return types. We didn't say some variable equals this method. We did not call any of these 3 methods for their return values because they don't even have a return type. They all return void. But they did affect the program. We called these methods for their side effects, and their side effects being initializing these variables, these instance variables on the heap. So after we call these methods, we see those changes because they were changed on the heap by following a reference, and the heap persists across stack frames. These stack frames are gone and didn't return anything, but during their execution, they went over to the heap and made some changes to variables on the heap. So now even when this constructor returns, we see all the changes, all the effects of those 3 void methods. So void methods are going to be very useful moving forward. And then the constructor ends, and what a constructor resolves to, we don't have to have any return values here. It's going to resolve this whole expression new simple player. This is going to resolve to a reference to the object that was created. That's the same with array lists, hash map, lists, dictionary. You've seen that before with your data structures, but it's the same thing here. When we create a new object, the constructor resolves to a reference to the object that was created, which will always match this keyword in the constructor. It's going to be a reference to that object that was created. And that's a constructor call. A lot going on. So let's run it back and do it again. So we have a new variable P2, and we're going to call the simple player constructor again. I'm going to go through it much quicker here because we do have a bit of a time crunch here. We're into the second portion of lecture by quite a bit. This, we are seeing the keyword new, so we're going to create a new object, simple player, map the constructor. We get copies of all the instance variables. That's a typo. HP and name. So copies of all the instance variables, and each of these objects have their own copies of these instance variables, which can vary independently of each other. This, we got we rolled OX200. And we have 2 constructor parameters, name and max HP. Name, which is Kane. I held shift, but my timing was off. And max HP, which is 14. We're going to go through our constructor, do all of our setters. This dot, now we can get it wrong because we have 2 objects, so we have to be careful about our references. This dot, and then from this object here, we're calling set max HP. So when we have set max HP, we have this as a reference to the object, wherever we were when we called that method, the calling object, which is OX200. And then max HP, which is 14 for this example. Then this dot max HP equals max HP, 14. Same thing we just did before, so I'll go a little quicker through it. Set HP, unless there are questions, of course, so I'll slow down to explain it, of course, as always. OX200 called this method as well, and HP equals 14. This dot HP equals HP. Oops. 14. Return. Then set name. this is OX200 name cane. The good thing is we're running low on new concept. There's a lot of concepts this lecture. This lecture is a heavy one. But the good news is we're running low on new things to introduce. So pretty much everything is out there, and we can spend the rest of the lecture, the second half of lecture, reinforcing everything that we just talked about, because I threw a lot at you. Public versus private, static versus non-static, objects and classes, constructors, the keyword this, and a whole bunch of use of references. There's a lot, and we're going to spend some time reinforcing all that now. Forgot my return arrow, because I always do. And the constructor, again, resolves to a reference to the object that was created. Whew. Okay. We got through those two constructors. I might change this example to not call the setters, at least not all three of them, because it adds a lot to the trace. And finally, we're on to this line right here. We've seen this with data structures, but we need a reminder because, my goodness, this is important. And I guarantee you'll see some code similar to this on your OOP trace, where there's going to be some number of objects created, and somewhere there's going to be an assignment like this to make sure you understand this concept. When we create this variable P3 and we assign it the value of P1, the value of P1 is the reference OX100. It is not an object of type simple player. It's not a simple player. No, it's none of that. It has nothing to do with this object itself. It only stores a reference to the object itself. What it stores are the instructions of where to find an object of type simple player on the heap. It is not the object itself. So when we have that assignment, what we do is assign the reference. The value of P1 is a reference, so what P3 gets is the reference. This is an assignment by reference, and that's it. That's all that happens on that line. We do not create a copy of an object. We don't create a new object. I'll see students go through everything we just went through twice. They'll go through it a third time on this line. Don't fall into that trap. Your trick for this is you see the keyword new, you're creating a new object on the heap, and I emphasized that when we talked about the keyword new. You see the keyword new, you know you're about to call a constructor, and you're creating a new object on the heap, and you're clicking this button right here to create that object on the heap. The opposite is also true. If you do not see the keyword new, so I don't see the keyword new on this line at all, that means you better stay away from this button. You're not creating a new object on the heap. That's not happening because you don't see the keyword new. So when you go through your code, what I like to do is a double check when we're done with a trace, especially if I'm submitting a trace for a grade. If I were in that position again, I'm going to look through my trace. I'm going to count the number of objects on the heap. I got 2 of them right here. And I'm going to look through my code and trace through it just really quickly. I'm going to look at how many times my code hit the keyword new. I see 1, I see 2. We're calling the constructor, but it looks like the keyword new does not show up anywhere else. So I'm not worried about the constructor creating new objects, which can happen. We'll actually see that in the next example. It might be 2 examples from now. We'll see it today. So I see the keyword new is hit twice, and I know these method calls, nowhere else in the code is the keyword new, so these method calls aren't creating new objects. And then I reach the end of the main method. So I better end up with 2 objects when I'm done with this trace, and I do have 2 objects, so I'm going to be good. I would do that check after I do the rest of the trace, but I have 2 objects, and I hit the keyword new twice. I'm feeling good. If you have this as a quiz, if I give you the OP quiz for the midterm, and you hand in your quiz, and this was the code will be more complex than this because we have to do inheritance also. But if this were the quiz and you turn in something with 3 objects on the heap, that's an easy instant fail. That's a fail all day. There's no question that you don't understand what you need to understand. You did not complete the learning objective if you think 3 objects were created in this code. So that's something I need you to understand. You've got to understand how objects are created, how constructors are called, how references move around in our code. That would not be a simple mistake because it's related to the 116 concept that we're covering. If it's related to a 116 concept, something that's explicitly stated as a learning objective in the syllabus, any mistakes related to those, they gotta be instant fails. So 3 objects on the heap, that's an easy way, like me, the TAs, whoever's grading it, we glance at that, we see 3 objects, we give you a 0 on that one. Easy grading. It's an easy job for us. But don't be in a position where we're doing that when we're grading yours. Double check 2 objects, 2 keyword news. I don't see the keyword new here. I'm not creating a new object. If you create a new object on this line, I know you don't understand what I need you to understand. Okay. What you should know from 115 anyway, that should be review, but it's something that, you know, I gotta gatekeep in 116. If you don't know that concept by now, you would fail 220 if I let you go there. So I need you to understand it before I let you go into 220 and fail there. Because I don't like students. I don't like seeing students fail 116, but at the same time, I can't just pass everybody and let them fail 220 and 250, because you're never going to go back to, students don't go back to a previous class that they passed to fill in the gaps so they can pass the next class, unless they're forced to. It's a sad truth. So then we have p1.setName, p1.setName, so we're calling setName from this object right here, ox100, setName. This is ox100. And we give the parameter setName name. It's going to be Paladin. And then this in setName, this dot name, this dot name equals Paladin. So we're going to replace that value same way we do with variables on the stack. We're going to cross it out and write in the new value, Paladin. Then that method ends. Then we're going to do p3.getName. p3.getName. So we're calling getName from this object. Happens to be the same object that we used on the line before when we did p1.setName. Now we're doing p3.getName. So getName, where this is still ox100. And there's no parameters. GetName is a getter, no parameters here. And it's going to return name. So this, oh, I don't have my this dot. I always like to be explicit with this dot. So now I have to talk about this. So if you don't have the keyword this, what Java will do is look in the stack frame for a variable with that name. And if it doesn't find it, it'll automatically follow the reference this and then look for the value, look for a variable named name in this case. It'll look for your variable. So we'll have some sort of progression where it starts in the stack frame, then follows the reference this and looks for an instance variable. I like to be explicit and always do this dot, just so my code's more clear what it's doing, that I am going to an instance variable. But if you don't do this dot, you can sometimes still have code that works perfectly fine. So sometimes it's optional, but not always. If you always use the keyword this, you don't have to worry about when it's optional and when it's not. It's not optional when you have a name conflict. I can't do max HP equals max HP, because now I will find the stack frame variable both times and never make it to the object. So this dot name is going to return Paladin, and that's what's printed to the screen. So notice what happened here. If you're looking at just the code, it can be easy to miss this. But we did p1.setName Paladin, and then p3.getName. If you're not careful with this, if you're just looking at the code and not the trace I think makes this very explicit, very clear. But if you're just looking at the code, it looks like you changed the name of P1 and then you're getting the name of P3. it's easy to think of those as two different objects because they're two different variables, and we would call this the player P1 and the player P3. But when we look at the trace, we know what's actually happening is P1 and P3 both store references to the same player object. And when we called P1.setName, we went over to that object and changed its name instance variable. And then when we got to P3, we did P3.getName. We get Paladin, not Dark Cecil, because we changed that name on the heap when we did P1.setName, and P3 and P1 are two variables that refer to the same object. So P3 does see that change that we made through P1 because they both refer to the same object on the heap. Very, very important to understand that one. Without that feature, without that functionality right there, there would be significantly less reason to even talk about references. But because we have this behavior, this is why you need to understand references, or else you're going to be really confused when you have bugs in your code. You're going to be really confused about why you have bugs if you don't know that, well, P1 and P3. Like, you might think that this is copying P1, because that's how ints work. That's how strings work, kind of. Strings are weird. That's how doubles work, that you would get a copy of the value because primitives store values directly. This primitive that's an int stores the literal int 10 in its variable, not a reference to an object that has the value 10. It stores the value 10 directly. But once we're messing with references, our variables just store references, not values. Very important difference. Okay, we are... I think that lecture does usually go over. Like by a significant amount. So I'm not worried yet. Let me just peek and make sure. Yeah, and then this lecture is pretty light. And this is one big memory diagram. Yeah, okay. There's just so many, the concept, this lecture is concept heavy, and a lot of the concepts, I just let them all rip right out the gate. So that first lecture takes forever because I'm explaining so much stuff. And if I don't take enough time to explain all those concepts, I mean, it already is overwhelming. It's going to be even worse if I just rip through it at light speed, which it might have already felt like it was going at light speed. So we're, for the most part, done with concepts. I do want to talk about encapsulation and another reason why we use public versus private. Did I? Yeah, I did getters and setters as a reason for public versus private. But another public versus private discussion. Other than that, we're pretty much done with concepts. I just want to reinforce everything we learned a couple more times. And that's usually my lecture style. I like to get all the concepts out there and then reinforce. So let's reinforce that and see everything we just talked about from different angles. And that different angle is going to be from the ArrayList class as an example. So we've been using ArrayList I say all semester. We've been using ArrayList for a week. And now that we know about classes, let's take a little bit of a peek into the ArrayList class and talk about how that works. So ArrayList, we created a new ArrayList, and that created an ArrayList object on the heap, and on the stack in our variable R1, we just stored a reference to that ArrayList on the heap, and then we can go over to the heap using the dot operator, follow the reference, and make changes to this object. Now we just saw that with a player object that we created, and that's the same thing that the ArrayList was doing. And when we created the new ArrayList, we called its constructor, and that's that special method that's going to create a new object. We see the keyword new. We know a new object is going to be created on the heap. We get, well, I already said this stuff. I got ahead of my slide already. But let's crack this open and see a little bit of how that works, because we know that's what happened. We called an ArrayList constructor that takes no parameters, and that created an ArrayList object on the heap, and it has instance variables. We just pretend that they're reference indices mapping the values. That's how we like to think of our array list. But what we know now that we wrote our own class, we know the array list object is going to have some number of instance variables that store values. So let's take a look at this. And I'm going to crack open the array list class itself. If you want to do this in your code in IntelliJ, control click, or on Mac, command click on the word array list. Let me do a very brief. So wherever you use an array list, do control click, and it's going to take you to the array list class, and you can take a look at all of the source code for the array list class. So if you're ever interested in looking through that, one actual, because usually, I mean, you don't have to care. That's one of the nice things about libraries and classes and methods is you can encapsulate things, a word I'll introduce in a few slides, that you can hide all the details and not have to care about how the array list class works. You just need to know that it works. As long as it does work, that's fine. That's enough for us. But if you ever do want to look at the code, and one reason you might want to do that, outside of curiosity, if you're curious, take a look at the code. But outside of that is to know all of the methods that you have available to you. We have the array list constructor, an array list constructor that takes a collection. This is the one we use when we do arrays.asList. We have size is empty. That's one we never mentioned in class, but you can see, does the obvious thing. If the size is 0, return true. Dot contains, so if you want to check if a certain value exists in your array list. Index of, index out of range, clone to array. There they are. Get and add. If you want to just see every possible method that's available to you, the answer is always going to be the source code. If you look through the source code, that is your definitive answer. You can search Google all day. Nobody's going to give you the definitive answer of what's in that class. You look at the source code, that is the answer. It cannot possibly be wrong because that's the code that you're using. So that's what we're going to do in the slides. But as you saw as I was scrolling, there's a lot of stuff in there. I'm going to do a very slimmed down example. I'm removing most of the code of the array list class so we can be a little more focused and look at the parts of it that I want to talk about in a more narrow view. So first, we know it's in a package java.util in a class named ArrayList, because when we import it, we do import java.util.ArrayList. So we know where to find it, the package and class name. That's a given. And then when we call the constructor, it took no parameters, so we know that the ArrayList has a parameterless constructor. And we can see that right here. I'm removing the code for now, but it's actually just one line. We'll get to it when we get in a few slides. So we know that there has to be a constructor, and there in fact is. Public ArrayList, it has to be named the name of the class, doesn't have any return type, and takes no parameters. So we know that exists because we can call it. This code compiles, it runs, so everything's fine. So we know that that constructor exists. We also know that a second constructor exists. So when we said new ArrayList and gave it this arrays.asList, we know there's a second constructor. There's a lot of syntax here that we're not going to talk about, but to interpret this means that it takes some data structure and it's going to pre-populate the array list you're creating with all of the values in that data structure. And for our purposes, we used arrays.asList and gave it a list, which asList actually does create an array list, but it uses the list interface, things we'll talk about when we get to polymorphism. And the important thing is a list is a collection. It's going to work for this constructor. So this question mark extends aside, it will just work. And that's the constructor we're using when we call this. And this is an overloaded method. This is something that's allowed in Java. You can have two methods with the same exact name, and the same exact return types. Actually, that doesn't even have to be part of it. But you can have two methods with the same name in the same class. That's allowed as long as they have different parameter lists. And then based on the argument list that you provide, that's going to determine which method is called. So since I'm giving it a collection here, I'm going to get the one that takes a collection. And if I give this no arguments, I'm going to get the parameter list constructor. I'm going to get this one. So which constructor is called is going to depend on which argument list I give it, and it's going to call the one that has a parameter list that matches my argument list. And we can do this for any method. We're actually going to see another example today. And we know classes have both state and behavior. And the state of the ArrayList class, the instance variables of the ArrayList class, has two of them, and one of them is a plain old array. So this isn't just a regular array. We've seen this syntax in the string array parameter of the main method. We haven't used arrays yet, and we won't. I won't use arrays at all this semester. But this is a plain old array. So an array list is effectively a wrapper for a regular, just plain old array. And it has a second, and then gives us more functionality on top of regular arrays, or else we would just use regular arrays. But array list makes it really nice to work with an array. If you work with arrays directly, they are not so nice. They're not as easy to work with. They really don't have much functionality at all. You can check its length, I think, is all you can do. And you can change values in specific indices. Importantly, you cannot change the size of an array. And an array list gives us the illusion that we can, even though we can't. And then we have a second argument, second instance variable that's tracking the size of the data structure, the number of elements that we have in this array list, which is not always equal, and often, most of the time, is not equal to the size of this array, so it has to be tracked in a separate variable. And we have a getter for size. We've called this before. We've asked an array list for its size, so we know that there is a method that exists called size. It returns an int, and it just returns this dot size, the value of that instance variable. So when we're creating our array list, we could technically put them on the heap with two instance variables, element data and size, because that is in fact what does happen. And then element data is a reference to an array, so when we create an array list, we're actually creating two separate objects. But we simplify that in our traces and just pretend that array list is pretty much just an array for our traces only. And then let's fill out this parameter list constructor. We have our constructors, which are going to initialize our instance variables, and we need to initialize this element data, our initial data for the data structure. And for the parameter list constructor, we're going to initialize it to an empty array, which we actually have stored in a constant here. There's a constant that just stores the empty array, and that's going to be the initial value of element data in the first constructor. In the second constructor, there's a bunch of code that it does what you would expect it to do. It iterates over this collection and adds all those values into an array and creates an array of an appropriate size. I'm not going to put all that code here, but this array list also initializes the instance variables, and this one will also set size to non-zero. So this code is actually using that default value. If you declare an int without assigning it, it will be assigned the value 0, and that's never overridden in this constructor, so size will just be 0. And this is the entire code for this constructor. It's just a one-liner. Sets element data to an empty array. This one does a bit more, but we don't want to get lost in the details here. And well, I thought I had a slide on it, so let me just mention it here. This is very similar to the epsilon variable we saw last time when we talked about testing doubles. Is we have a private variable. All these instance variables are always private, of course. But we have a private variable that's static and final. So private means we can't access it from outside this class. So this is a variable that's only useful for this class. Just like epsilon was, we made epsilon private because we only needed it in that class. Static means it belongs to the ArrayList class itself. Final means it's a constant. That's why it's spelled in all capitals here. That's how we signify that this is a constant, making our code more readable. And it's of type object array, and it's equal to an empty array. So we have a private static final. This is a variable that belongs to the ArrayList class. So when we say default capacity empty element data, this is accessing that variable from the ArrayList class itself. This is the same as saying ArrayList dot default capacity empty element data. It's the same thing as saying that. So we could put ArrayList dot here. The source code doesn't, but it would be the same exact thing. That's what it's doing. Because it's static. It belongs to the class. And final means we can't reassign it. We can never say default capacity empty element data equals something else. We can't reassign it because it's final. Okay, and yeah, I thought I did. And then on this slide, I actually do ArrayList dot. So we can modify the code here that does the same exact thing as it did before with ArrayList dot because it's accessed through the class itself because it's static. And then the add, get and add methods. So we have these non-static methods. These are called through objects of type ArrayList. So when we have an ArrayList object, we do your variable name that stores a reference to that object, dot get, dot add. You're calling these methods through that object, not through the ArrayList class. So these methods are non-static. These are not static methods. And we have our second overloaded method. The add method is actually overloaded in the ArrayList class. The public one is the one we call. It just takes the thing you want to add. And that's what we like. We want to call this method that's just, here's the thing that I want to add, and that's it. But it is actually overloaded. All this method does is actually calls the overloaded method that takes 3 parameters and does some extra stuff. Takes the element data and size from the instance variables and then does some magic. And this is private. This is a private helper method. So it helps the developers organize their code and, for whatever reason they wanted to create the second method. I'm sure there are reasons. I can speculate as to what they are, but there are reasons to do this. And they make that private because nobody has to care about this method's existence. Nobody has to care. You've never wondered this up until this point. You've never known or cared about this because you don't have to. And that's a wonderful thing that we don't have to. And it's and in a few, let me skip ahead. And that's a wonderful thing. I'll come back to that one. And that's a wonderful thing that we don't have to care about this. And this is something called encapsulation. And we love encapsulation, specifically in object-oriented programming. This comes up a lot. Is where we hide the details and expose a public interface. So everything that doesn't really matter to the end user, we can make private. Like, you never had to care about this default capacity empty element data. You never have to care about this. You never have to care that an ArrayList actually uses an array under the hood and that it has a separate size variable and doesn't just take the size of that array, or that it has this overloaded add method with 3 parameters. At no point in time where you're saying new ArrayList add stuff, ArrayList.get, when you're working with your ArrayList, at no point do you ever have to care about any of this stuff. So the developers make it private, hide the details using something called encapsulation. Encapsulation is our fancy word for saying hide the details. And don't make everybody get bogged down with all of these implementation details of how the ArrayList class works. Just expose the public parts of it and say, look, this is what you can do with an ArrayList. So hide all these details, this stuff that no one ever cared about if they just want to use an ArrayList. a lot of us care about it out of curiosity, like how does an array list actually work? And then we want to go dive deeper and take a look at it. And in 250, you'll explore all this stuff in great detail, like what's this grow method doing, what's happening here. I'm not going to talk about that in 116. Sometimes I do, but we're at a time crunch right now. We don't have to care about any of this stuff. So we can choose to care, but we don't have to care. That's the important distinction. And then anything that we do want to care about, that people do care about, we're going to make public. And these are the methods that we've cared about since day one. When we work with array lists, these are the first things I show you. Okay, the constructor that takes no parameters. We eventually talked about the second constructor to make your, just to clean up your average, the problem set.average testing. It's a little cleaner if you use this one. .size was in our first example. .get was in our first example. .add was in our first example. These are the methods that you're going to use all the time when you're using an array list. So those are public. Those are exposed to you. This is your API. This is how you're going to interact with the array list code, is through its public API, through all its public methods. API meaning Application Programming Interface, which is a term we really overuse in programming quite a bit. But in short, API, this is how two pieces of code interact with each other. So your code is going to interact with this code by calling these public methods. Your code is not going to interact with it by calling any of the private stuff. For one, you can't, but it's private because you don't have to, and you shouldn't call those methods. Those are implementation details that nobody has to be concerned about except the person writing the array list class. So this is another reason we have public versus private. It's to hide the details and make your code simpler to use for other people because they're not exposed to all the little details of how you got that thing working. All right, let's jump back to this slide. I don't have a ton to say about it, but I wanted my stuff to flow. Anyway, the keyword this is a reference to the object that called the method. And this is important, for example, the size method. When you call the size method on an array list, you want the size of that specific array list. If you have 5 array lists in your program and you call .size on one of them, you want the size of that array list. So it makes sense that the keyword this is a reference to the object that called that method, so we can get the size of that specific array list. Without the keyword this, size isn't going to know which array list you want the size of. This is how the size method knows, oh, you want the size of this array list, the array list that called this method, because you did array 3 dot size. So you must want the size of the array list being referenced by the variable array 3, and it knows that by using the keyword this. Since it has a reference to the object that called that method, it knows which array list you want the size of, and it goes to that array list, this dot, go to that array list on the heap, and get its size instance variable and return it. And the keyword this makes that possible. If without the keyword this, you have 5 array lists and you call .size on one of them, Java just has to guess which one you want the size of. With this, it has a reference to the one you want the size of, and it can get the size of that specific array list. Okay, and static, I just want to, I always forget the order of these slides, and I want to do them in I should just reorganize these slides and do them in the order that I naturally do them in when it's go time. All right, so static, I already talked about this, but static means it belongs to the class. So this variable belongs to the class. So this is the same as not having array list. Java will go through its progressions. It won't find this variable if you don't have array list dot. It won't find this variable in the stack frame. It's not a parameter. It's not a local variable. It's not going to be in the stack frame. So it'll continue its search to this dot, and it's not going to find it there either. So then it's going to continue its search to the class itself and look for a static variable with that name. It will find it here and then use that variable. Or you can be explicit and do array list dot. And by the way, when I'm not going to say non-static method all the time. From this point forward, if I say method, I mean non-static method, because that's going to be 98% of our methods moving forward are going to be non-static. So I'm just going to say method. Moving on. Except today, I'll still say non-static a bunch because that's new to us. But by the time we get to linked lists next Tuesday, I'm just going to start calling them methods, including on the homework assignment. If I say write a method on the homework assignment, I mean a non-static method, and I'll explicitly specify if it should be static, but if I don't specify anything, that means non-static. And whew, this is quite the lecture. There's so many concepts, and we're done with the concepts at this point. But I want to talk about how they're applied in different instances. Reinforce, reinforce, reinforce. And one way to show that again is the math class. This is a very shortened version of the math class. Math class is one that's pretty helpful to look at the source code for, because you can see all of the methods. There might be some methods available to you that are quite useful that you might not know exists if you don't look at them. So the math class has a lot of static stuff. No, I can't say that. Just about everything in the math class is static. The math class is made to be a collection of methods that you call that basically act as functions. Just like our problem set from task 1, the math class is basically like that. It's a collection of static variables and is a library of just these, or static methods, these methods that we can call. Like absolute value is the one that we saw so far, and that's a public static method that takes an int and returns an int, returns the absolute value of that int. But it is static. That's how we did math.abs. We called it through the class itself because this is a static method. If it were not a static method, we would have to say new math, store that in a variable, and then that variable's name .abs, and call it through the object of type math, through an object of type math. But since it's static, we call it through the math class itself. So we do math.abs, just like we do problem set.average, problem set.sum of digits. Same thing with math. Math has a bunch of static methods. Math.abs, math.pow, math.tangent. We call them through the math class themselves. And math also has the rare public variable. It does have some public variables defining some useful constants for us. If you want to use pi in your code, in your Java programs, never type 3.1415. Eventually you're going to get sick of writing digits and you're going to have some truncated pi. Use math.pi. It has a public variable available to you. Use math.pi, and that gives you pi to the precision that can fit in a IEEE double. So this gives you exactly the best precision that you can have in a double for the value pi. And same with e as well. If you're using e in your code, use math.e. Don't type out your own e. Don't create your own e variable. Use math.e. Now, math gets away with public variables here. This is pretty much the one exception in Java where you can have a public variable, and that's when the variable is final. Since the variable is final, this is just defining a constant, not an actual variable that will vary. It's a constant. There's no harm in making this available to everybody because nobody can say math.e equals and change it on you without using a getter or setter. They can't do that because they'll get an error because it's final. So if you have constants, there's no harm in making those public. And I don't know why, this trips me up, but why they made degrees to radians and radians to degrees private. I wish they would make these public so we can just access these variables, but instead we have to use pi and calculate them ourselves. If they were public, we could just use these variables. It'd be, another handy thing that the math class could give us, but for some reason they're private. Even though there'd be no harm in making these public. Okay. Public versus private, static versus... Oh, one more thing with the math class. I said almost everything's static. This is also a rare case of a private constructor. Usually your constructors, you don't want them to be private, there are some cases where you want private constructors that do actually do things that are called from methods inside of that class itself. There are strange cases, but they do come up. But math is doing something else here. It's making a private constructor because it does not want to be instantiated at all. It does not make sense to say new math in Java the way this is set up. Doesn't make sense. So the developers said, you know what? We're not going to let anybody call the constructor. We're going to make this a private constructor and say you're not allowed to create a new instance of the math class. It's all just a collection of static stuff. Say math.e, math.pi, math.absolute value. Don't ever create a new math. So it's not even going to let you create a new math object because it's not what this class is made for. If they just delete this, you might say, well, why not just not even write a constructor? Why create a constructor just to make it private? It's because if you don't write any constructor, you get what's called the default constructor, which is the same thing you see here. It's parameterless. It doesn't have any parameters and doesn't do anything. The body is empty, except it is public. So if you don't write a constructor, you do get the default public, no parameters, no body constructor. So in your code, there's no reason to do this, but in your task 1, you can say new problem set and create a problem set object. It's not meaningful. It doesn't do anything because everything in there is static, so there wouldn't be any reason to. But you can do it because you get the default constructor because you didn't write any constructor, because there's no reason to write a constructor, but you do get a constructor. So math says, no, we don't want the default constructor. Do basically the default constructor, but make it private so nobody can create a math object. No, it doesn't. So abstract class is a whole other thing. This actually, math could be abstract. It wouldn't change anything, to be honest. Wouldn't change anything if math was abstract. If they said public abstract class math, wouldn't change anything. But it isn't abstract, but it's not abstract only because they didn't put the keyword abstract here. That would be another way of doing this. If you did abstract, then they wouldn't have to have this private constructor because nobody can create an object of that type anyway if it's abstract. It would be another way of getting the same effect. But they went with a private constructor instead, which I like because it's neat and I get to talk about it without having to talk about abstract classes quite yet. But abstract classes can't be instantiated either. So that would be the same, another solution to the same problem of not letting anybody create objects of that type. Okay, and I don't have a memory diagram today, right? Okay, we're almost ready for, yeah, this is a good catch-up lecture, even though we didn't get caught up. All right, and kind of a side topic, but I mean, I got to bring it up some point, and I don't want to wait all the way till inheritance to bring this one up. But we will revisit this when we get to inheritance. Is if you print out to the screen, you can print everything to the screen in Java. You can convert anything to a string and print it. And if you print your object to the screen, what you'll get is this garbage right here. You're going to get the fully qualified name of the type of that object, which is its package plus its class name, the @ symbol, and then some randomish value. It's random to us. It's semi-related to the reference on the heap of where you can find this object, but it isn't exactly. It's obfuscated through the JVM, and it's weird and stuff. But it's some unique identifier for this object, regardless. And this is pretty much never what you want. You don't want this. Like, that's just garbage. I don't think I've ever had a case where this was useful. So what you can do, if you want something more meaningful, is you can write a toString method. If you write a method exactly like this, it returns a string and is named exactly toString with a capital S and takes no parameters. Everything has to be exact. If you write a method like that, Java will see what you're doing here and it'll say, I know what you want. You want me to call this method when your stuff's printed to the screen. Or you could call toString directly also. Uh, but it's going to call toString when you print something to the screen, and whatever string this method returns, that's what you're going to get printed to the screen instead. So if you want better behavior when you print your objects to the screen, which can be helpful for debugging purposes, when you print, you don't want just that garbage from the previous slide. You want something more meaningful to your objects, and we can do that with a toString method. And a reminder, we created a new type. I said this in a slide in bullet points, but here I get to actually emphasize it, is since we created a new type of type player in the last set of slides, we can, I didn't emphasize it here. Oops. I should have mentioned this in the other, in the memory diagram, is that we can have variables of that type. So we have variables of type player. I didn't explicitly mention, but we did use that quite a bit. We have variables of type player. We have parameters of type player. We can have return types. I don't have it in this code, but we can have return values of type player. And we can have data structures of type player, which we will see in the example we're about to do. So we can use this player type wherever we can use any other type, because we just defined a new type in Java. So Java is strongly typed, and it's like, well, what happens if you don't have the type that I want? I want a type that has HP and max HP and a name and attack power. What if I want that as a type? Well, you create a new type. You create a type, you give it whatever instance variables you want, whatever state and behavior you want, and now you have a brand new type in Java of your own creation that you can use wherever you can use any other type. So we're not stuck with array list, hash map, etc. We can create our own types. Very powerful. Okay, and I think these slides are just, I'll double check just to make sure something's not slipping my mind. I have to have 3 regular lectures of content all in my brain for these things, so sometimes things slip. But 2.5 hours of content I have to have preloaded in my memory. But I think we're just, composition garbage collection. Yeah, I guess I'll do the slides just to talk about those. Composition, it's a concept. Some people just like their big fancy words. But this is an implication of things that we've already talked about. But if you hear somebody say composition, they're just trying to be fancy, in my opinion at least. Sometimes I'll use this word just to make it, I don't know, usually it doesn't matter. Not in the context of coding, but in the context of education. I'll be like, oh, that's the lecture where we talk about composition. That's the only time I use this phrase, because everybody's going to know what I'm talking about then. But composition is when you have a class with an instance variable, and that instance variable is another class type. So I have an instance variable of type array list. That's composition. Just means I have an instance variable that's not a primitive. If somebody says composition, that's just an implication of, okay, well, my variables, I created a new type in Java. My variables can be of any type. Instance variables can also be of any type. Instance variables are just variables. Instance variables can be object types. It's just an implication of all that stuff. So we are going to see that in the trace. We're going to trace through this code that you see here. It's going to take me a second to set up in the tracing tool. Not too long, but it's 2 classes I have to cut and paste. And then garbage collection. This is something we're not really going to talk about much. Like, I'll bring it up now. And I'll bring it up later if, at one time in linked lists, I think I mentioned it. And if anybody asks questions, I'll talk about it. It's no harm in talking about it, but it's not a learning objective. It's not something you need to know to do well in this class. But it's something nice to know. Where garbage collection is, well, let me say what it is first. So if you lose all your references to an object on the heap, that object is going to be garbage collected by Java. Java is going to free up that memory and make it available for other heap objects. So when I create this character and assign it to this variable hero, and then I immediately take hero and assign it a new reference to a different character, I can no longer access this first character I created. So this first character will be garbage collected. There'd be no reason to do these 2 lines like this ever in the real world. I'm only doing this as an example to talk about garbage collection, but we wouldn't actually do this specific thing in the real world. So this code is just dumb code, but it's made to talk about this point in a lecture like this. In the real world, I would never write code like that. So it is garbage collected. Where garbage collection is really going to be extremely important to your lives is in CSE 220, where you're writing in C. That course is taught in the programming language C, which does not have garbage collection. So, and garbage collection is one of those things where you don't ever really have to think about it until it's gone. And once it's gone, you will miss the garbage collector. This is such a powerful, important thing that helps us write code much, much easier. C doesn't have it, and that's for good reasons why the course is taught. And one of the reasons that the course is taught in C is because you have to learn how to manage your own memory. That's like a lot of the stuff that you're learning. Those are learning objectives of that course. If you use the language with garbage collection, they just wouldn't be able to teach 220 effectively. So 220, a lot of it is about memory management, and you're going to lose that garbage collector, and you're going to realize how much it's been making your life easier this semester. And last semester, Python has a garbage collector as well. And it really, really, really makes your life easier. I like my garbage collectors. I don't like managing my own memory. All right, so we need the party class. Trash can, all that. Party class. And character. Where's my mouse? There it is. And I'm gonna start trimming these things down a little bit. We don't need package declarations at this point. I can get rid of some blank spaces. Let's see if we can get this whole thing on the screen at once. Oh, it's a little more than I even had to. Let's add a few more spaces in, just for readability's sake. Okay, so here's our code. We have a character that's going. How are we doing on time? 23 minutes. We'll get as far as we can. As long as we get to this line, and I can explain this line once, that's the one I really want to talk about. There's a lot of other things that are important here that are reinforcing things that we saw in the last trace, but this line is confusing enough. If you can understand this line, you're doing fantastic. So I want to make sure I get to that one. Character, it's going to track its battles won and experience points. Party, which is going to have an array list of characters and track its battles won. This is like an RPG. I'm thinking of like a JRPG where you have a party of characters. You fight battles, and each character has their own experience points to track when they're going to level up. And we're also going to track the battles that each character won, as well as how many battles they won as a party. So with that, let's start tracing through this thing. Everything starts with the main method. We have the variable hero. And we're going to run this from the party class. There's no main method in character anyway, so we're going to start at the main method in the party class. Hero is assigned a new character. Make sure I spell this right. My return arrow, I see the keyword new, so I'm creating a new character. Character has battles won and experience points. Neither of them are initialized through the constructor. They're both just initialized inline, so I'm going to give them their values right away. EXP points 0. This we got OX100. Character, the constructor does nothing, takes no parameters, does nothing. It's just the default constructor, so this just returns right away and returns OX100 to the heap, to the stack. And the next line, we do it again. We're going to create a new character. Battles 1, 0, EXP points 0. We got OX200. My return arrow returns to here. This returns replaces this value with OX200. Remember, when we cross out anything in a memory diagram, that means that value is actually erased from memory. It does not exist anymore. So since we replace that value OX100, nowhere from our stack do we have access to this object at OX100 anymore. We cannot reach it. We have no possible way, nothing we can do, no code that we can write after this second line executes that lets us access this object again. It is completely lost to us. Whenever this happens, Java's garbage collector is going to say, look, you can't even get to that object anymore because you lost all your references to it. I'm going to clean that up for you, and it's going to remove this object from memory. We don't have a way to indicate that in the tracing tool, but it will actually be erased. And it'll be erased at an unknown time. We don't know when it'll be erased. It's up to Java to schedule the garbage collector and have it happen at some time. But we don't know when. But we cannot reach this character anymore. It's effectively gone to us, and once the garbage collector runs, it will be literally gone. It'll be erased. That memory will be freed up for another object. Okay, let's do this again. Fighter. Character returns to fighter. This character, the red constructor, battles 1, 0, EXP points, 0. This was OX300. This returns OX300. That's our fighter. Then hero.win battle. So hero.win battle. So we're calling win battle from this character right here. So win battle, since we called it from that character, this is going to be OX200, a reference to the calling object. And then win battle of 10. I know the argument is going to be 10. I don't know what the parameter is yet because I didn't look, but hero.winBattle. And this brings up our next, I guess you could call this a concept, but our next thing we have to talk about, because this is the first situation where this is going to come up, is we have two methods called winBattle, and we have to know which one to call. This will be a theme, today it'll be a theme in inheritance, and it'll be a theme in polymorphism. We always have to know which method is being called, and the method that's called is going to depend on the type of the object that called that method. This is called from OX200, so it was called from an object of type character. So we're going to look in the character class for a method named winBattle that takes an int, and we find it right here. We find our parameter is xp. And this dot battles 1. This dot battles 1 plus plus, so we increment this by 1, and then this dot experience points plus equals, so we're going to add xp to it. Xp evaluated from the stack frame. Each expression we start over at the stack frame is going to be 10, so 0 plus 10 is 10. This returns, and we move on to the next one. We're creating a new party. So let's do our fourth constructor here. I can see, oh, actually I don't want this line. I added that line, I accidentally pushed that to the repo. Somebody had a question one last semester, and I guess I accidentally pushed that code. All right, so we're gonna create a new party. So we have party. We're calling the party constructor. We have the keyword this. We're creating a new party. Map the constructor. I got OX400. I have my return arrow going here. And party, I got to look at all of the instance variables. We have an instance variable members, which doesn't get initialized, so I'm not going to give it a value yet. And then battles 1, which is initialized to 0. And then we're ready to call the constructor. It looks like it has no parameters, so all we have is this, which is a reference to the object being created, and no other parameters, so nothing else goes in the stack. Don't make that mistake of putting members in battles 1 on the stack. They don't go there. Your instance variables do not automatically go in the constructor stack frame. Constructor has no parameters, doesn't get anything except the keyword this in that stack frame. And then we run the method this.members. So this.members equals new array list. And whenever a method, so there is an array list constructor that goes on the stack, that it does actually happen. Whenever there's code like that that's internal to Java, we're not going to trace it. So if it's internal to Java, and your shortcut for this is if you don't see the source code in your quiz, you don't have to trace it. I didn't give the array list constructor code in this example. That means we're not going to trace it. It's internal to Java. You have to know that this will create an object of type array list, but you don't have to trace what happens, because if you don't have the code, like how do you know what this method is going to do? This one happens to not have any parameters or local variables, but if it has parameters, I don't have any examples in this code, but if it had any parameters, how do you know what their names are? How do you know what to put on the stack? You know the argument, you know what values they're going to get, but you don't know what they're called. You don't know if that method creates any local variables. You don't know if it calls other methods. There's no way for you to know that, and I'm not going to make you memorize that for all the standard methods that we use, like ArrayList.size also. We're not going to trace this because we don't have the code for it. We can't trace it. We can't do it. Now, in these just so happens that those two methods, we did see the code earlier today. So we can infer what they're going to do. We know we could trace these, but I'm not going to make you memorize all that stuff. You're not going to have to memorize it. You do have to memorize what these methods do, but not how they do it. So we know this is going to create a new array list. So we have our array list on the stack. We don't map any constructor because we didn't trace the constructor, and it doesn't have any variables in it. So I'll trash can the variable, but we did get the reference. That's what we need here, OX500. And this is why I even mentioned composition, is when we have that, we are going to have references to objects on the heap that have instance variables that they themselves have references to other objects on the heap. And that's why composition gets its fancy word, is because you are doing a bunch of bouncing around the heap to get to where you need to go. So party has an instance variable that is a reference to another object. That's perfectly allowed. It's a thing called composition. This constructor returns, and we get OX400, the object that was created, back onto the stack. All right, then party.addCharacter. So we have an add character method call. This, and I always get in the habit when I put a frame on the stack, I'm going to do this right away. It's actually kind of tough in the first few lectures where I'm not doing this on the frames where they're static methods. I have to kind of unlearn that for a few days, but I always put this right away. Add character, so we have party.addCharacter, party OX400, dot means take me to your object. Add character, so from this object we're calling add character, so this is OX400. And the parameter is, the argument is hero. This is a separate expression evaluated from the stack frame. Hero is OX200, so I know the value is going to be OX200 here. And add character from the party class, its parameter is called member. And then what the code actually does is this.members.add member. This is our first line with multiple dot operators. We have since we're using composition here, we can and will sometimes hop around the heap quite a bit. So we have this, and you're going to see this quite a bit where a method has nothing but references. It's a lot of references moving forward. this dot members, which resolves to OX500. So this dot members resolves to OX500, and dot means whatever's to my left is a reference. Take me to your object. That's still true, even though what's to the left is an expression that it itself had a dot operator that went to the heap. Doesn't matter. Whatever's to the left is a reference, which is OX500 right now. Dot, take me to this array list, and then add that member. Member is another expression, so we start over at the stack frame. Member is OX200. And the add method that's internal to Java, there was an example, I missed this one. That's internal to Java. We don't trace it because, yeah, we know what the argument is, but what's the parameter name? We don't know. What does add do? Add actually calls a helper method, and that helper method has 3 parameters and does all kinds of stuff and calls the grow method sometimes. Like we don't have to trace that. I'm not going to make you memorize all that. And then we have a variable, so at index 0, we're going to get that OX200. And this returns. We do it again, add character. This, same thing for the next one, except we're going to add that fighter. Fighter is OX300. So member is OX300. This dot members dot add, the value fighter member from the stack frame is OX300. And this returns. Then win battle. This is the one we're here for. So we got to it. Which we got 9 minutes. Oh, we're doing good. Party dot win battle. So from this object, we're calling win battle. So we have win battle. Let's get what we know out here. Win battle. This is OX400, a reference to the object that called the method. We know the argument is 20. And then we have to find the parameter. So win battle, which was called from OX400, which is an object of type party, means that we're looking in the class party for the win battle method this time. So we're not getting this win battle in the character class. We're getting the party's win battle. So party.winBattle is this one that takes an int. This one right here, this is the method that we're calling, and our parameter is XP. And then this dot battles 1, this dot battles 1 plus plus. Then we hit a loop, and now we're getting into it. We're going to create a code block for the loop. Remember, code blocks exist. X is 0 for the initialization statement in a for loop that's created in the context of that loop's code block. So x equals 0. X0 is less than this dot members dot size. This dot members dot size is 2. 0 less than 2 is true, so we're going to execute the loop and get to this line. I said we need to get to this line. We got to it. We might even finish this whole trace. Yeah, we might get there. We're doing the damn thing. All right. So this line right here, this one's a doozy. So let's go through this one. If you understand this line, if you can trace this line, you are doing great. You're most likely passing the OOP quizzes. Of course, we have to talk about inheritance and get the rest of it. But if you can understand this line, you're going to understand inheritance just fine. And so let's go through this. So this, that much is easy. This resolves to OX400. Dot means take me to your object. So we're going to the object. By the way, when I say understand this line, I'm confident that every one of you can look at this code and get a good idea of what this code's going to do. We're going to go to each of the characters in the party and increment their battles 1 and experience points. The XP will be incremented by 20. And the party stuff, we already did it. But like that's the effect that we're going to have. I'm confident you can all read the code in that sense. Like get an intuitive feel of what it's doing here. But can you trace through every single step of how it does that? Why exactly that is the behavior? So if I give you a method that's not so intuitive, would you still be able to trace through it? Because there's a lot of just context that we have a party winning a battle and we're going through the members. There's a lot of context you can take advantage of to read this code because the code is legible, because I like to think I did a decent job of writing the code in a clear, concise way. But if it wasn't, would you still be able to read it? That's what I mean by understand this line. Just so you know, just to make sure that's clear. So let's go through this. This results to OX400. Dot means take me to your object. And then at this object, we're resolving the variable members. So we're getting the instance variable members, which resolves to OX500. So this resolves to OX500, just like it did in add character. Now we're calling dot get. So dot, we were at OX500. We said dot, that means take me to your object. And we're going to call the get method from this array list. Get is internal to Java, so we're not worrying about tracing the get method. But we're going to get x. Kobe. So we're going to get x. And x is a separate expression. You can think of this with your PEMDAS from math. This is inside the parentheses, so actually this does have to be evaluated first. X and XP have to be evaluated first, and these are separate expressions. So when we do evaluate these, even though I'm reading this left to right, this is evaluated first, and when we evaluate these separate expressions, we start over at the stack frame again. So even though when we're calling the get method, we're calling it from this array list, so we bounced over memory to get to this array list, when we resolve x, that's resolved from the stack frame. There's only one x in memory right here anyway, so we can't get this one wrong. But that's if there were multiple x's as instance variables and whatnot, we need to start over at the stack frame to get the value of x, which is 0. So when we call get at this array list, we're getting the value at index 0, which is OX200. So this whole thing right here resolved to the reference OX200. And then we keep going. We have another dot operator. That means what's to the left of me resolved to a reference, the reference OX200. Dot means take me to your object. So we're following OX200 to its object. So we're at this character object right here when we call win battle. So when we're putting this win battle on the stack, this is going to be OX200. And then its parameter is going to be assigned XP. We start over at the stack frame again. We're in the win battle stack frame at this point. The parties win battle, this one right here, XP is 20. So our argument is going to be 20. This is called from a character. So we go to character for win battle. Its parameter is XP. And then we're finally ready to run this method call, which is just the same as when we did hero.winBattle. We're going to do this dot battles1 plus plus. This dot experience points plus equals XP 30. And this returns. Yeah, let's finish this thing. That returns. That's the end of the loop. We increment x. We check our condition. X 1 less than 2 is true, so we do it again, and we're ready to do this line again. This dot members dot get x, which is 1. Get the value of x is OX300 dot win battle. So we're calling win battle from this character, which is OX300. So this, for this method call, is OX300. That's a character. We go to the characters win battle. XP is still 20. This dot battles 1 plus plus. This dot experience points plus equals 20. This returns. That's the end of our loop. The code block for the loop ends and x is no longer in memory. Then immediately after, the method itself ends. which brings us back to the main stack frame. This just resolved. Then we hit the closing brace for our main stack frame, and the program ends. And we got there just in time, 10:29. Whew. It's hard to time a 2.5 hour lecture. I was getting a little worried at the beginning there, but we got caught back up. I think this usually does. Like Monday spills over into most of Wednesday. I think that is just how this week usually goes in the semesters. I think I have to rebalance the timing on the lectures and just play into that, since I end up adjusting every time anyway. All right, and it's 10:30. Whoo, baby, look at that timing. All right, so that's lecture today. I'm gonna take a half-hour break, eat some lunch, and do it again. Yeah, I don't. Trying to think if I have any other announcements. To those of you who didn't even start task 1, I'm sure you're not in lecture anyway, so there's no point in me saying anything about that. All right, yeah, have a good day, Dave. Thank you for that, and have a good day, everyone else. Take care. I'll see you Tuesday, if I don't see you in office hours at 2 o'clock today. Take care, everybody.